here to really pull back the curtain on some complex topics, sort through the noise, and give you those key insights. Today, we're looking at something you probably handle without a second thought. A rope.
Seems simple, right?
Exactly. Seems simple, but think about it in a high-voltage setting. You'd probably assume, well, it's synthetic, it's fine. Non-conductive.
A very common assumption.
But what if that rope, the one used for support, for lifting, for safety, what if it's actually a hidden danger? What if everything you thought you knew about rope safety is, frankly, dangerously out of date? Okay, let's unpack this. Today's deep dive is all about a huge shift, really, in rope safety, especially around energized equipment.
It's more than just new gear. It's a mindset change.
Absolutely. Moving from just assuming something's safe to actually verifying its reliability. That's the core of it for electrical workers. So our mission today, figure out why those traditional ropes just don't cut it anymore. What makes a real dielectric rope safe?
And maybe explore why they aren't everywhere yet, the barriers.
Yes, the surprising barriers. And then the best ways to use and look after them. We want to give you that shortcut, that critical info on an evolution that genuinely saves lives. So let's kick things off by tackling that big assumption. For years, decades maybe, standard synthetic ropes, polyester, polypropylene ones, often with waxy finishes.
Yeah, common ones.
They were just assumed to be non-conductive because, well, plastic doesn't conduct electricity, right? Simple as that. How's that holding up?
It's a belief that's really rooted deep, isn't it? But
Yeah.
what's fascinating and honestly quite concerning is that the real-world testing tells a very different story.
Oh.
Yeah. While the base material itself, the plastic polymer might be an insulator, the rope as a whole is different. Think of it like a sponge.
It's almost ribbon,
When it's dry, fine. But expose that traditional rope to moisture, rain, humidity, even sweat or dirt, oil, grime. It soaks it up.
Right.
And once it does that, those insulating properties plummet. It basically becomes contaminated.
So it can conduct electricity then?
Potentially, yes. It transforms from what you thought was a safe tool into a hidden hazard. It's a silent change, but a critical one.
That sponge effect.
Yeah.
It's far more significant than people realize.
Yeah.
So what happens when this goes wrong? What are the consequences of this lack of awareness?
It's led to some really dangerous situations. We've actually seen instances of false marketing, ropes claimed to be dielectric or insulating.
But without the proof.
Exactly. No rigorous testing behind it, just a label. Imagine trusting your life to that.
Wow.
Then there's the other risky idea that if, say, a half-inch rope passes a test, then a 3/4-inch rope of the same type is automatically fine too.
Doesn't work like that.
No way. Electrical properties change with size, construction, everything. You can't just extrapolate. And of course, just routine exposure, water, mud, oil. It always compromises a traditional rope's insulating ability.
And these weren't treated like other safety gear?
Historically, no, not with the same care as, say, hot sticks or FRP tools. Your insulating gloves get tested regularly, right?
Yeah.
Ropes often didn't get that same level of scrutiny. So a key part of the safety system was basically an unknown quantity, untested, unverified.
You might be listening and thinking, wow, I never thought a rope could be a hazard like that. And that's exactly the point. It's not about blame. It's about uncovering a risk that's now being properly addressed.
Yeah.
So we've identified the problem, the hidden danger. Now, this is where it gets really interesting. What's the solution? How do we get to verified safety?
Okay, so this is the big shift, the arrival of the true dielectric rope. And true is the key word here.
What makes it true?
It's fundamentally different because it's designed specifically for electrical insulation from the start. Then it's tested rigorously against tough standards. And finally, it has to be maintained just like any other critical insulating tool.
So it's the whole life cycle.
Exactly. Design, test, maintain. It's a system, not just a product.
And this rigorous testing, what did that actually look like? What guarantees reliability?
We're talking serious testing. High voltage withstand tests, tests to check resistance to contamination, tests to make sure it keeps insulating over time, even when wet.
Wet testing, too. That sounds important.
Crucial. And it's all governed by specific global standards. Think organizations like IEC, they have one called Live Working Insulating Ropes.
Okay.
And ASTM with their standard for unused rope with special electrical properties. Plus, you've got guidelines from IE on maintaining energized lines and even broader safety standards like NFPA 70E or Canada's CSA Z462 on arc flash. They all fit together.
So these aren't just suggestions. They're like rule books.
Pretty much. They define what safe actually means in measurable terms. They ensure these ropes can handle real-world electrical stress. It's the difference between hoping it's safe and knowing it's safe.
Right. And how do these ropes fit into the bigger safety picture for workers?
Well, if we connect this to the bigger picture, they're becoming a really integral part of the whole electrical safety system. Right up there with hot sticks, FRP tools, rubber gloves, arc-rated clothing.
So another essential tool in the kit.
Exactly. And interestingly, they're not just adding to the kit. In many cases, they're actually starting to replace things like FRP tools for certain jobs.
Really? Why is that?
They offer some pretty compelling advantages. Think about it. Lower weight. That's huge if you're climbing a pole or a tower.
Easier to handle, yeah.
Often lower cost over the long run because they might be more durable or easier to maintain.
Right.
More flexibility and length. You can get exactly the length you need.
Versatile.
And often enhanced load-bearing capacity compared to an equivalent FRP tool, all while giving you that top-tier insulation. So better safety and potentially better efficiency. It's a genuine step up.
Okay, so it's not just about the rope itself, but how it integrates. Given that, what are the absolutely essential practices? How do you make sure a dielectric rope stays safe throughout its working life?
That's a great question, because the best design means nothing without proper handling. Our sources point to four main pillars of best practice. And what's interesting is how much they echo practices for other critical safety gear. It really underlines that these ropes are safety tools.
Okay, pillar number 1.
First, verify compliance with recognized standards. Don't just take someone's word for it.
Check the paperwork.
Absolutely. Make sure the ropes meet your local standards. Ask the supplier for test reports, for certification. You want proof of lot traceability. Where did this specific batch come from? And crucially, it's leakage current performance.
Leakage current.
Yeah.
That's how much electricity gets through.
Exactly. You need documented proof that it's incredibly low, well within safe limits, even under stress. That's your electrical guarantee.
Makes sense. Pillar 2.
Second, store and maintain them like other insulating tools. This is critical. They aren't just any old rope you toss in the back of the truck. After use, they need to be cleaned if necessary and stored properly. Think clean, dry, well-ventilated space. Away from contaminants, oil, grease, chemicals, even excessive dirt.
Protect them.
Yes, and inspect them regularly, clean them, and get them periodically retested dielectrically. When transporting, use sealed containers or protective bags. Treat them like the precision safety instruments they are.
Got it. Pillar 3.
Third, inspect ropes before each and every use. This is non-negotiable.
Every single time.
Every single time. A quick visual check, look for cuts, burns, fuzzy spots from abrasion, chemical contamination, excessive dirt. If it looks damaged,
Don't use it.
do not use it, period. And this ties into the periodic electrical testing, too, to catch anything the eye might miss.
Okay. And the final pillar.
And fourth, arguably the most crucial, train your workers. You can have the best ropes, the best procedures, but if the crew doesn't understand the why and the how...
It falls apart.
Right. Educate them on the risks of using the wrong rope, or a contaminated one, near energized lines, and provide specific hands-on training for the actual dielectric ropes they'll be using, handling protocols, inspections, storage, the whole package.
And emphasize they're like hot sticks. Treat them that way.
Precisely. It reinforces that these aren't just ropes, they're life-saving insulating tools.
Okay, so this seems like a clear win. Better safety, clear standards, defined practices. So why isn't every utility, every contractor using these exclusively? Despite the obvious benefits you mentioned, adoption has been, well, slower than expected. What's holding things back?
That is the million-dollar question, isn't it? And our sources dig into this quite a bit. It really shows how hard it can be to shift long-held beliefs, even when safety is on the line. We see about 6 common barriers cropping up repeatedly.
6 barriers. Okay, let's hear them.
The first one is pretty straightforward. Resistance to change. Simple inertia.
We've always done it this way.
Exactly that. Some safety folks, some supervisors, they genuinely think the old synthetic ropes are good enough. They might say, well, we haven't had a rope-related incident in years, or maybe incidents just aren't properly documented or understood.
But that overlooks the hidden risks, contamination, degradation.
Precisely. They're often working with a reactive mindset. The critical point they miss is profound. Just because a road hasn't failed yet doesn't mean it's actually safe. That's the hurdle.
Okay, barrier number 2.
This one's really dangerous. The assumption, we always work de-energized.
But things aren't always truly de-energized, are they?
No, that thinking ignores so many risks. Induction from nearby lines is a big one. Accidental re-energization, maybe a switching error, maybe lightning, even customers backfeeding the grid with improperly wired generators during an outage.
That happened.
It does. We've seen cases where ropes became energized during what everyone thought was dead work. The only truly safe approach: treat every system as potentially live. The consequences of being wrong are just too severe.
That makes sense. Barrier 3.
Third is dismissing wet testing. People say, oh, we're in a dry climate, or we don't work in the rain, so wet testing dielectric ropes isn't relevant for us.
But you said wet testing was crucial.
It absolutely is. It's not just about rain. Wet testing is the best way to find hidden contamination during periodic checks. Even in dry areas, tools get dirty, oily, maybe stored in humid conditions.
So it revealed problems moisture alone wouldn't.
Exactly. It's the ultimate stress test. It proves the rope can maintain its integrity even when conditions aren't perfect. It gives you confidence regardless of the weather.
Okay, what's barrier number 4?
This involves incorrect assumptions about the technology itself. Some employers, even workers, might think, oh, these new dielectric ropes. They'll need special tools, tons of retraining, major changes to how we work.
They see it as complicated or niche.
Yeah, they get the impression it's this specialized thing only for rare situations. But the reality is, many manufacturers design these ropes to work seamlessly with existing hardware and standard work practices. It's about enhancing safety within the current system, not necessarily completely changing it.
Gotcha. Barrier 5.
Number 5 is the tough one: financial hurdles and reactive safety cultures. Let's be honest, high-performance dielectric ropes often cost more upfront than standard ones.
The initial price tag.
Right, especially when you add in the testing and inspection costs. And in organizations with a more reactive safety culture, meaning they tend to react after an incident rather than proactively preventing one, that initial cost can be a major sticking point.
But they're missing the bigger picture.
Completely. They overlook the potential costs of an accident, the human costs, obviously, but also legal fees, reputational damage, downtime. It adds up fast. Forward-thinking organizations see safety gear like this as a preventive investment, not just an expense. They know it pays off.
That's a crucial distinction. Investment versus expense. Okay, the last barrier, number 6.
Finally, there's what you might call administrative complexity. Just the thought of navigating new standards, updating purchasing procedures, implementing new tracking protocols. It can seem overwhelming for safety departments or procurement teams.
Bureaucracy can slow things down.
It can feel daunting, but the good news here is that, as we mentioned, the standards for dielectric ropes align really well with the frameworks already in place for things like FRP tools, insulating gloves, arc flash gear.
So you're not starting from scratch.
Not at all. It's more about integrating these ropes into existing safety management systems, adapting current protocols, rather than building a whole new bureaucratic mountain.
That's a really important point. It's often about leveraging what's already there. So it seems these barriers are less about the ropes themselves and more about, well, inertia, assumptions, and maybe process challenges.
Largely, yes. Though the cost is a real factor for some, the high-performing groups find ways to justify it through that investment lens you mentioned. They do cost-benefit analyses that factor in accident avoidance.
And they tackle the admin side by adapting, not reinventing.
Exactly. Smart integration is key.
Okay, so we've mapped the dangers, the solutions, the hurdles. Let's bring it home. How do we make absolutely sure we're maximizing the safety and reliability of these critical tools? It's not just about buying them, right? It's about consistent best practice. And of course, always follow the manufacturer's instructions to the letter.
Absolutely. And again, these practices should feel familiar if you're already handling other insulating tools correctly. It's about extending that same level of care. Let's quickly recap those 4 pillars.
Right. Pillar 1 was verify compliance, check the standards, get the test reports, know that leakage current number, proof, not just promises.
Perfect. Pillar 2. Store and maintain them properly. Clean, dry, protected storage. Treat them like the precision equipment they are, away from contaminants.
Pillar 3. Inspect before every single use. Visual check for any damage. Cuts, burns, dirt. If it looks wrong, don't use it. Simple as that. And periodic dielectric testing.
Couldn't say it better. And pillar 4. Train the crews. Make sure they understand the risks, the specific ropes they're using, and the correct handling procedures. Treat them like hot sticks.
Got it. So we've really covered the whole journey here, from those dangerous old assumptions about regular ropes
The hidden hazards?
to the verified, tested reliability of true dielectric ropes. It's a massive shift driven by standards, by testing, and it's all about preventing injuries in these high-voltage environments, moving towards genuinely proactive safety. So what does this all mean for you listening right now? Whether you work in the field, manage safety, design systems, or just care about keeping people safe, being informed makes a difference.
A life-saving difference, potentially.
Understanding that gap between just assuming something's safe and actually verifying it, that's key.
Yeah.
It's about fostering that proactive culture, not waiting for something to go wrong.
And, this whole journey with ropes, from overlooked risk to verified reliability, it's a powerful reminder, isn't it? It makes you think. What other tools, what other processes, maybe even in completely different fields, are we just assuming are safe?
That's a good question.
Where else might we be operating on outdated beliefs or insufficient data? This whole deep dive encourages that kind of critical thinking, questioning assumptions, demanding verification, especially when safety is involved. Good enough? Often isn't, really.
That's a fantastic point to end on. A call for vigilance everywhere. We definitely encourage you listening to think about that. What other assumed safe things in your world might need a closer look, a deeper dive? Thank you for joining us on The Deep Dive.
It's been a pleasure.
We'll see you next time.
The views, information, and opinions expressed during this podcast are solely those of the individuals involved and do not necessarily represent those of Utility Business Media and its employees. It is strongly recommended that you discuss any actions or policy changes with your company management prior to implementation.